Hey there, welcome to Graph Theory with Python Part 3. In this video, you'll learn how to visualize graphs using Python. Along the way, you'll learn about special families of graphs and how to write some Python functions that will generate those for us. Before we get started, if you haven't seen parts 1 and 2 of this series, I'll put a link to the playlist right up here. I highly recommend you check those out so you'll be caught up and up to speed with what we're going to talk about today. And if you'd like to download the code that we're writing in this series, you can find it on my GitHub page. I'll put a link to the repository on the screen and also down in the video description. All right, let's get started. There are several ways you can visualize graphs using Python. In this video series, we're going to use a package called pyvis. It's built on the Viz.js JavaScript framework and it integrates beautifully with Jupyter notebooks. Let's switch to an editor window and I'll show you how to get it installed. Here we're looking at the terminal windowed in Visual Studio Code. I'm in the same directory as the graph.py file that we made in the last video about adjacency lists and adjacency matrices. The first thing I'm going to do is create a new virtual environment. That will allow me to isolate pyvis and its dependencies and keep them separate from any other packages I have installed on my system. To do that, I'm going to use the venv module in the standard library. I'll start by typing the Python 3 command, followed by the -m flag, then the word venv, and then the name that I'm going to give to the virtual environment directory, which I'm going to call .venv. I can also use the prompt flag to give it a name separate from the directory name. I'm just going to call it Python graphs. When I run this, it will create a virtual environment in a directory called .venv with a prompt name called Python graphs. Now I need to activate the virtual environment. I can do that by running a script that's already been created for me in the .venv directory. I do have to execute it using the source command though. Now my virtual environment is active, and you can see the prompt name Python graphs shown here before the prompt in my terminal. If you've never worked with virtual environments before, or you're a little rusty and need to relearn a few things, I highly recommend checking out RealPython's article or video course on virtual environments. I'll put a link to that in the video description. Now that we've activated the virtual environment, the very first thing I'm going to do is upgrade Python's pip package manager. This is really important. Using the latest version of pip will help make sure the installation process goes smoothly. All right, now that pip is updated, we can install pyvis. To do that, we're just going to run a pip install pyvis. You can see that pyvis has quite a few dependencies. This video was recorded on Pi Day, or March 14th, 2021. I have no idea what year it is when you're watching this, so I don't know what the current state of these packages is. In order to make it so that you can follow along and recreate the exact environment that I have here, I'm going to freeze all of these dependencies into a text file called requirements.txt. I can do that using the pip freeze command. That creates a text file called requirements.txt containing all of the dependencies and exact version numbers that I installed in this video. Here's what the contents of that text file look like. Okay, great. We've got pyvis installed. Now we can actually visualize some graphs. Let me show you how that works. Let's start by opening a new Python 3 shell. The first thing I have to do is import the network class from the pyvis.network module. The word network here is being used as a synonym for graph. That's because graphs are great at modeling networks. First, I'll create a new network instance. Let's call it net. Now that I have a new network instance, I can add nodes to it using the add_node method. Let's add two nodes, one called 0 and one called 1. To add an edge between nodes 0 and 1, I use the add_edge method. Add_edge has two parameters, one for each of the nodes the edge connects. So I'll pass to it 0 and 1. Alright, so this gives us a really basic graph, one with two nodes and one edge connecting those nodes. Now we can go ahead and visualize it. To do that, I'm going to use the show method. I'm going to pass a string to show that contains the name of an HTML file. That's because pyvis generates a static HTML file that you can open in a browser to view and interact with the graph. Let's call it basic.html because it's a pretty basic graph. Now, this doesn't immediately show anything, but I can go ahead and quit the REPL session and then open that HTML file to see what it looks like. First, let's see if the file was actually created. Yep, there it is. Basic.html. Let's go ahead and open that. When I run the open command, it opens up my internet browser and shows me the graph. And here's what it looks like. We have our two nodes, 0 and 1, with the edge connecting them. One thing that I like about pyvis is that the default styling looks pretty good. I can even interact with the graph by clicking and dragging around vertices. Pretty cool. Pyvis even works with directed graphs. Remember, a directed graph is one in which the edges have a direction to them. They point from one node towards another one. And we usually indicate this by adding a little arrow on the edge that indicates the direction. Let's head back to the editor and I'll show you how to visualize a directed graph. I'll open another Python 3 shell. Then I'll import the network class again and create another network instance called net. However, this time, before I create the instance, I'm going to set the directed attribute to true. Now I'll add two nodes, 0 and 1, and an edge that connects 0 to 1, starting at 0 and pointing in the direction of 1. Finally, I'll call the show method and pass to it the same string we did before. Now I can head back to my browser, refresh the page, and I should see the directed version of the graph show up. Look at that. Nice. We can also add multiple edges and loops to a pyvis graph. Let's head back to the editor again and add a few of those. I'm going to continue working with the same network we've just defined. I'll start by adding a new edge that starts at node 1 and points in the direction of node 0. Now I'm going to add two loops, one on the node 0 and one on the node 1. This adds the loop to node 0, and this adds the loop to node 1. I need to show the graph again, so I'll use the show method and pass the basic.html string to it again. Let's head back to our browser and hit refresh to see what that looks like. Pretty cool. One thing to note here is that instead of showing two edges between 0 and 1, it shows one edge but with two arrows on it. That's fine. Okay, now that we know a little bit about pyvis, let's see how to write a Python function that takes a graph object, that is, of the graph name tuple type we defined in the last video, and returns a pyvis network instance ready to be shown. I'm now looking at the graph.py file we created in the last video. We've got our graph named tuple type, our adjacency dict function, as well as our adjacency matrix function. Below the adjacency matrix function, I'm going to define a new function that allows us to visualize graphs created from the graph named tuple type. I'll call that function show. Let's give the show function a parameter called graph, and I'll scroll down to give us a little bit more room on the screen. The show function will do two things. It's going to create a new pyvis network instance and then call that network's show method in order to create an HTML file that we can open in a browser to visualize the graph. Let's start by creating a new network instance, and let's call it G. We haven't imported pyvis into our file, so right now VS Code doesn't know what this network thing is. Let's move back to the top of the file and add the right import. Alright, now that that's imported, we're ready to work with our new network instance. We need to add all of the nodes in the graph to the network. We could write a for loop that loops over each of the nodes in the graph's nodes list and uses the add_node method to add them to the network. But there's a little bit shorter way that we can do this. Pyvis networks have a method called add_nodes with an S on the end. That method accepts a list of nodes to be added to the network. Let's go ahead and use that now. Remember, graph.nodes is a list of all the nodes in the graph, so we can just pass that to the addNodes method to add all of the nodes in the graph to the pyvis network. Now we need to add the edges. Just like there's a plural for the add_node method, there's also a plural for the add_edge method, add_edges. Let's use that to add all of the edges in the graph to the pyvis network. Now we're ready to show the graph, so we'll call the show method on our pyvis network instance. Since show requires the name of the HTML file to save the visualization to, let's add a parameter to the show function called output_filename. And we'll pass the argument passed to output_filename to the pyvis network's show method. Now, this is already enough for us to show a graph, but let's do one last thing. Let's return the pyvis network instance from this function. That way, if we want to, when we call show, we can assign that to a variable that'll allow us to work directly with the pyvis network instance if needed. Okay, we're almost done. There's just one thing missing. Right now, this function assumes that graph is undirected. So no matter what, pyvis is going to treat graph as an undirected graph. Remember, we can control whether or not the pyvis network is directed by setting the directed attribute when we create the network instance. The directed attribute should be either true or false. And our graph objects have an attribute called isDirected, which is set to either true or false. So we can just assign the value of graph.isDirected to the directed parameter of the pyvis network. And last but not least, let's document what this function does in a docstring. All right, let's take our new show function for a spin. I'll go ahead and open up my internet browser and put it side by side with my terminal window so that we can see both the code and the output at the same time. I'm going to run the graph.py file in interactive mode using the -i flag. That will execute all the code in the file and then drop me into a Python shell where I can interact with the code. Let's create a graph with 4 nodes, 0, 1, 2, and 3. We can do that by using the range function. Now let's define a list of 5 edges. The first edge will be between the nodes 0 and 1. Then we'll add an edge between 1 and 2, an edge between 2 and 3, and an edge between 3 and 0. Finally, let's add an edge between 0 and 2. Now we can create a new graph object using the nodes and edges list we just defined. Let's call it G. And let's make this an undirected graph. Now we can visualize the graph using the show function we just wrote. Let's name the output file basic.html. That way all I have to do is refresh my browser to see this new graph. Alright, we see some output in the terminal. That's because the show function returns the pyvis network instance it uses to visualize the graph. That's what we're seeing here. Over in our browser, we can refresh the view to see the new graph. And there we go. We see the 4 vertices, 0, 1, 2, and 3, and the 5 edges we defined. And since pyvis creates an interactive visualization, we can drag these edges around a little bit. Okay, now let's check and make sure the show function is working for directed graphs too. Back in our interactive shell, let's recreate the graph G with isDirected set to true. And now let's pass G to the show function again using the same output file name basic.html. When we refresh our browser, now we see the directed version of the graph. Now, pyvis gives you pretty extensive control over the style of the visualization. You can change the colors for nodes and edges, adjust the fill for nodes, even give nodes titles. For our purposes, in this Graph Theory with Python video series, we're not going to get into all that. What we have here will work just fine for us. But if you'd like to see a video explaining in depth how to use pyvis, let me know in the comments below. Actually, I'll tell you what, if I get 50 thumbs up on this video, I'll do another video that explains pyvis in way more depth. All right, let's stop for a second and take stock of everything we've done so far in this series. And if you're enjoying this video, please give it a thumbs up. It really helps me out. And consider subscribing to my channel and clicking the bell icon to get notified whenever I release a new video. So far, in this Graph Theory with Python video series, we saw how graph theory got its start when the mathematician Leonhard Euler solved the 7 bridges of Königsberg problem. Then we learned about the precise mathematical definition of a graph and how to represent graphs as data structures in a Python program using an adjacency list or an adjacency matrix. And now we've seen how to visualize graphs using the Python package pyvis. We've developed some tooling that's going to help us investigate graph theory and use Python to produce examples and make observations that'll help us discover new things about graphs. But before we can get into proving anything about graphs or really going deeper into our investigation, it's going to be really useful to have some families of graphs in mind, things that we can quickly visualize and work with to get a feel for the kinds of things we're investigating. In the rest of this video, I'll introduce you to a few families of graphs that'll be really useful to know about. The first family of graphs that we're going to talk about are called paths. The word path is a really descriptive name. Here's what the path on 3 vertices looks like. Here's the path on 4 vertices. And the path on 5 vertices. Now we're going to introduce some notation. We call this family P sub n. We write it using a capital P with a subscript lowercase n. The lowercase n refers to the number of vertices in the path. And of course, the capital P stands for path. We can sort of standardize paths by agreeing to visualize them as a straight horizontal line. And we can label the vertices, or nodes, starting with 0 up to n-1, beginning with the leftmost node. Using the P sub n notation, we can also give each of these paths a name. For example, the first one is P3, the second one is P4, and the third one is P5. I started with P3, but there are 2 smaller paths. P2, for instance, is a path on just 2 vertices, and P1 is a path on just 1 vertex, which might seem a little odd because it's literally a graph with just 1 node and no edges, but we still call it the path on 1 vertex. We could also call P1 the trivial graph, and you'll hear it commonly referred to this as well. It's trivial because it only has a single node and no edges, so there's really not anything to talk about. Another important thing to note here is that all of these are undirected paths. That is, none of the edges have a direction to them, so we're not drawing any arrows on them. Because paths have such a nice structure, we can actually explicitly write out in a general way what the nodes and edges of a path are. The vertex set V for a path on n vertices is just the integers 0 through n-1. The 3 dots, or ellipses, in my set just indicate that every number in between 0 and n-1 exists in this set. Now, if n happens to be 1, the path on 1 vertex, then it just contains a single element, the number 0. For P2, it contains the numbers 0 and 1, and so on. We can also explicitly describe the edge set. Now, for the path on 1 vertex, or the trivial graph, the edge set doesn't have any elements. It's called an empty set. But for anything else, it's always going to contain the edge 0, 1. And for paths on 3 vertices or more, the edge 1, 2. All the way up to the edge n-2 to n-1. That's the edge that connects the last 2 nodes in the path. So these are undirected paths. They're a pretty basic family of graphs, but they're still a good one to know because when we talk about more complex ideas in graph theory, we can come to these very basic examples to see if we can wrap our minds around how it works for something like this family of paths. And while we're talking about paths, let's head back to our editor and write a Python function that returns a graph representing a path on any number of nodes we want. We're going to write a function that takes an integer representing the number of nodes in a graph and returns a graph instance representing the path on that number of nodes. I'm going to call the function pathGraph. This function will have 1 parameter, the number of nodes in the path. I'll call it num_nodes. And I'll scroll down to give us a little bit more working room. Like all functions, it needs to have a docstring, so I'll write one now. Remember that the vertex set for a graph Pn is the set of all integers 0 up to n-1. I can create that using a range. Now remember that the edge set looks something like this. I'm using a Python list to represent the set, but that's okay because that's what edges needs to be anyways. The problem is to write this using Python code in a way that's clear and easy to understand. There are a couple of ways to do it, but I'm going to use a list comprehension. I'll do this by describing an edge in terms of an index I. Each edge has the form I plus 1. So if I start with the number 0, the first edge will be 0, 1. Then when I increments to 1, the next edge will be 1, 2, and so on. We're going to do this for all numbers I in the range up to num nodes -1. Now you might wonder why the -1. The numbers in this range stop at num nodes -2, which means that the last edge in this list will have num nodes -2 here, and then num nodes -2 plus 1, which is just num nodes -1 here. That's exactly what we want. Now that I have that, all I have to do is return a new graph instance using those nodes and edges. And since this is an undirected path, we'll set isDirected to false. Now there's one problem here. We talked about the path on one vertex, which we would create by setting num nodes to 1. But what happens when we try to create a range using the number num nodes -1, which in this case will be 0? Let's open up an interactive shell real quick and see what happens. So the range function will take the number 0. Let's see what that looks like as a list. It's actually an empty list. That's because the range really starts at 0 and ends at 1 less than 0, which is -1. Well, that doesn't really mean anything, so it's an empty list. Going back to our function, let's make sure this is going to behave the way we expect. If num nodes is 1, then we will create a list of nodes containing the numbers ranging from 0 up to 1 less than 1. That has just one number, 0. That's right. For our edges list, we're going to create the set of all edges that look like this for every number in the range num nodes -1, which is 0. That's an empty range. So that means the edges set will end up being an empty list. Again, that's exactly what we want. So everything works out just fine, and we don't have to worry about setting num nodes to 1 causing any kind of issue. But what if we set num nodes to 0 or -1? This doesn't make any sense. So we'll add a little bit of logic to raise an exception whenever num nodes is strictly less than 1. Okay, so here's what we've done. If the num nodes parameter is set to 0 or less, then we're going to raise a value error that says num nodes must be positive. This is good practice just to make sure that everything is going to work correctly in the function. We're also using an f string, which is a Python 3.6 and greater specific string interpolation method. If you're not familiar with f strings, I'll post a link in the video description to an excellent reference for them. In f strings, I can include this little bit, which when printed to the command line will print num nodes equals followed by the value of num nodes. This is just to help in debugging. That way we can see what value was passed to pathgraph if anything goes wrong. That might help us figure out where an error is. There's one last thing that could go wrong. What happens if I pass an argument, say the string math is awesome, or the number 3.14 instead of an integer? In that case, things are going to go a little haywire. So we need to check that num nodes is actually an integer before we do anything. We can do that using the isInstance function. And if num nodes is not an instance of an integer, we'll raise a type error. So what we do here is first check whether or not num nodes is an integer. And if it isn't, we raise a type error that says num nodes must be an integer and displays the type that num nodes actually is. Again, that's just to help us debug in case anything goes wrong. The real meat of this function are these 3 lines here, where we create a range containing the numbers 0 up to num nodes -1 and the edges in the path graph. Directed paths are a lot like undirected paths, except that the edges have a direction to them. However, they can't just have any direction. So let's talk about what directed paths look like. Just like undirected paths, we visualize directed paths as a straight horizontal line. Here's the directed path on 3 vertices. The thing to notice here is that the direction of the edges points from the vertex on the left towards the vertex on the right, and that is always the case. For example, this graph is not a directed path. That's because if I start on the leftmost vertex and try to get all the way to the rightmost vertex, I can't do it without violating the direction of an edge. By convention, we're saying the direction should be from left to right. However, take a look at this directed path. In this case, the arrows point from the right to the left. However, these really are the same graph. We'll talk more about this idea of two graphs being the same in a later video. For now, just know that I could turn the graph on the bottom into the graph on the top by just rotating it 180 degrees. Now, I would have to relabel the vertices to make it look exactly the same, but you get the idea. The code for creating a directed graph looks basically exactly the same as for an undirected graph. The only difference is that we're going to set the isDirected attribute of our graph instance to true. Let's head back to our editor and code the function that returns a directed path. Now we're going to create a function that returns a directed path on the number of nodes we specify. We could write an entirely new function, but we don't really need to. The only difference between a directed path and an undirected path from our perspective is that the graph instance that we create needs to have isDirected set to true. To handle that, we'll add a second parameter to the pathGraph function called isDirected. By default, we'll have this set to false. That way, if we call pathGraph without specifying isDirected, we'll get an undirected path. If we do set isDirected to true, then we'll get the directed path back. But it doesn't quite work as needed right now. We need to head down to where we return our graph instance, and instead of setting isDirected to false, pass to it the value of isDirected that was passed to the function. There we go. Now we have a nice function that will return both undirected and directed paths for any number of nodes that we want. The next family of graphs we're going to talk about are called cycles. Just like for the family of paths p sub n, the lowercase n here represents the number of vertices in the cycle. Now you might be able to guess from the name cycle what it looks like. Let's draw an example of a cycle on 4 vertices. The defining feature of a cycle is that I can start on any vertex, say this one, and walk along an edge, say going in the counterclockwise direction, and walk across every node and every edge and back up where I started. This cycle has 4 vertices, so we'll label it C4. We could also draw C5 and C6. Now, cycles are in some ways closely related to paths. If I remove one of the edges on a cycle, I'm left with a path. So when we explicitly write out the vertex and edge sets, they're going to look kind of similar to paths. The vertex set V will always contain the nodes 0 through n-1, and the edge set will always contain the edge 0, 1, 1, 2, n-2, n-1, and that gives us an edge set that looks exactly like the path, but we need one more edge, an edge between n-1 and the node 0. And finally, remember, we're talking about undirected cycles here. Now that we know how to describe the vertex and edge sets, let's jump back to the editor and write a function that returns a cycle for any number of nodes we want. Now let's write a function that returns an undirected cycle. I'll call that function cycleGraph. This function will have one parameter, the number of nodes. Like all of our functions, we need a docstring that explains what the function does. And I'll scroll down so we have a little bit more room to work with here. We're actually going to reuse some of the code from the pathGraph function. In fact, a cycle is just a path that connects the 2 end vertices with an edge. So we can actually start by creating a pathGraph instance. Let's do that and call it base path. Now that we have the path, all we have to do is add the edge that connects the last vertex in the graph to the first one. The last vertex in the graph will have the value numNodes minus 1. So all we need to do is add the edge numNodes minus 1, 0. Now all we have to do is return that graph. One of the advantages of reusing the pathGraph function is we don't have to do any type checking or validation on numNodes. That will be handled for us automatically when we call the pathGraph function. Now let's talk about directed cycles. Just like directed paths, directed cycles have every edge pointing in the same direction. Now it doesn't quite make sense to talk about left and right here, but we could say, for example, that we always draw our nodes in a circle and draw the arrows pointing in, say, a counterclockwise direction. So here's an example of the directed cycle on 4 vertices. Now, I just drew those edges pointing in the clockwise direction. That's all right. What's important is that the direction of the edges is always going the same way, around in a circle like that. Here's an example of a directed graph on 4 nodes that is not a directed cycle. The issue here is that if I try to walk along the edges of the graph following the direction of the edge, I can't start at one vertex and end up back where I started without violating one of the edge's directions. Coding the function for directed cycles works just like for undirected cycles. We just have to set the isDirected property of our graph instance to true. Let's hop back to the editor and see how to do that. Rather than writing a new function that returns a directed cycle, we can just modify the cycle graph function to handle that for us, much like we did with the directed paths. We'll add a second parameter called isDirected and set it to a default value of false. Then we'll just pass the value of isDirected to the path graph function. In order to create the cycle, we append an edge to the edges list in the base path. The edge that we're appending starts at the vertex numNodes -1 and ends at the vertex or points towards the vertex 0. That fits the definition of a directed cycle, so we don't need to modify anything here. And there we go. We now have a cycle graph function that works equally well for undirected and directed cycles. The next family of graphs we'll talk about are called complete graphs. The notation we use for this family is a capital letter K and a lowercase n subscript. The easiest way to describe a complete graph is where you take a set of nodes and add every possible edge between them, excluding multiple edges and loops. For example, here is the complete graph on 4 vertices. Every single vertex, like this one here, is adjacent or has an edge connecting to every other vertex, like these 3 here. And that's true no matter which node I pick to start with. Here's what the complete graph on 5 vertices looks like. Just like paths and cycles, the vertex set for the complete graph contains the elements 0 through n-1. The edge set might be a little bit trickier to describe. We can start by adding all edges connected to the first node 0. That would include the edge 0, 1, 0, 2, all the way up to 0 n-1. Now we can describe all the edges connected to node 1. We've already included the edge connecting 1 to 0, so we don't need to write that again. Remember, complete graphs don't include multiple edges. So we'll start with the edge 1, 2. Then we would have to include the edge 1, 3 if we had a vertex labeled 3, and so on up to the edge 1 n-1. Now we have to add all of the edges that are connected to vertex 2. We've already got the edges connecting 2 to 0 and 2 to 1, so we don't have to write those again. We would start with the edge 2, 3, all the way up to the edge 2 n-1. We would continue doing this until we finally get to the node n-2, and when we get there, there would be only one edge left that we have to add, because we would have each other edge connecting to n-2 already included in the lists above it. So the only edge left to add would be n-2, n-1. So the edge set for complete graphs looks a little bit complicated, but really all it is every possible edge between every node, excluding multiple edges and loops. One thing to remember here is that we're focusing on undirected graphs. A directed complete graph is called a tournament. Unlike paths and cycles, there are many ways to orient or direct the edges in a tournament. So we won't be able to write a function that returns a tournament or the tournament on n vertices for us, because there could be multiple tournaments on that number of vertices. We will talk about tournaments in later videos, and when we get there, we'll talk about ways to describe orientations, that is, the directions of the edges, and how to write some functions that'll allow us to create tournaments. But for now, let's just focus on the undirected version, the complete graph. Let's jump over to the editor and write a function that returns a complete graph for any number of nodes we want. Now we're going to write a function that returns the complete graph on any number of nodes. We'll call the function completeGraph. This function will have one parameter, the number of nodes. And as usual, I'll give it a docstring. Now I'll just scroll down to give us a little bit more working room. And in this case, we don't have an existing function we can call that will also handle validation for us. So we need to repeat that validation. We need to check that numNodes is an integer and also that its value is greater than 1. We've already got that logic in the pathGraph function. I could just copy and paste it into the completeGraph function, but we really shouldn't repeat ourselves. I'm going to write a new function that checks whether or not some value is acceptable for representing the number of nodes in a graph. I'll scroll up and put that above the pathGraph function, and I'll call it validate numNodes. The reason that I'm using this leading underscore is to indicate that this is a quote-unquote private function. That is, this function will be used by other functions in my graph.py file, but it's not something I expect to be used anywhere else. This function needs to have one parameter, the number of nodes, and of course it needs to have a docstring. The code for the validate numNodes function, I'm going to just copy and paste from the pathGraph function. And now in my pathGraph function, all I need to do is call the validate numNodes function. And there we go. Now pathGraph is still validating whether or not numNodes is correct. And now we can reuse validate numNodes in our completeGraph function. Great, so now we're checking whether or not numNodes is a positive integer. The next thing we need to do is create the set of nodes for the graph. Just like paths and cycles, that's the set of all integers from 0 up to numNodes minus 1, so we'll just use a range. Next, we need to create the set of edges. And this is where it gets a little bit tricky. Let's write a for loop that loops over each integer in the range from 0 to numNodes minus 1. You can think of this loop as representing each row in the set of edges we defined when we were explicitly writing out the edges in a complete graph earlier. When I is equal to 0, we'll build all edges containing 0. When I is equal to 1, we'll build all edges containing 1, except any edge we already created previously. When I is equal to 2, we'll build all the edges containing 2, except for any ones previously defined, and so on and so forth. In order to do that, we need to write a second nested for loop. Now here we have to think a little bit. The second index, j, needs to start at one more than the index I. That's because when the index I is 0, this for loop is going to create the second element of each edge containing 0. The first one will be 0, 1, so it needs to start with 1. Now when I is equal to 1, we need to create each edge containing 1 that hasn't already been created before. But when I was 0, we created the edge 0, 1, so we don't need to create that edge again here. There's also no loops, so we don't need to create the edge 1, 1. So we need to start with j equal to 2, or I plus 1, which I have a 1 here and need to fix. This range needs to extend all the way up to the number numNodes minus 1, so the second argument to range will be numNodes. And finally, inside this nested for loop, we're going to append the edge I, j. Now, writing the for loop this way may look a little bit confusing, but it kind of mimics the way you might draw a complete graph. First, you start at node 0 and draw every edge connected to 0. Then you move to the vertex 1, draw every edge connected to 1, but there's one you don't have to draw because you already drew it. Then you move to vertex 2 and draw every edge connected there, but there's 2 that you don't have to draw because you already drew them. So in a sense, this is kind of an intuitive way to define it, but it is not the most efficient. Nested for loops are pretty slow, and if we're looking at a complete graph with millions of nodes, this might take a while to create. There's a better option, and it requires understanding a little bit more about math. See, there's something called a combination. If I have a set of 4 things and I want to create all possible combinations of 2 things out of that set, those are called 2 combinations. Now, I could talk forever about what combinations are, how many there are, and things like this, but none of that is really relevant to us here. The point is, there's a function in the itertools module in the Python standard library called combinations. We give it a set or a list of things, in this case, the nodes in the graph, and tell it what size we want the combinations to be. In this case, 2, because we want every edge, every possible pair of 2 things in the set of nodes. That will generate all of the edges for us in a single line of code and much more efficiently than this nested for loop. So we'll head up to the top of our graph.py file and import the combinations function from the itertools module. Now I can head back down to my complete graph function and replace this entire for loop with a single line. we'll call the combinations function. The first thing it needs is an iterable or a list of things we're going to take the combinations from. That's going to be our list of nodes. The next thing it needs is the size of the combinations to make. Since we're making edges, which are pairs of nodes, the size needs to be 2. That's going to generate all the edges for us. Pretty nifty, huh? The only downside is that it doesn't return a list, but that doesn't really matter. We can turn it into a list by wrapping this whole thing with the list function. And there we go. We've just replaced a nested for loop with a single line of code. I'm a huge fan of the itertools module. If you're not familiar with it or you're a little bit rusty, I'll post a link in the video description to an article that I wrote for RealPython on the itertools module. Now that we have our nodes and edges list, all we need to do is return a graph instance built from those nodes and edges. And since complete graphs are undirected, we'll set isDirected to false. The final family of graphs we're going to look at are called stars. We use the notation capital S and subscript lowercase n-1 to denote the star on n nodes. This might look a little confusing, but remember, this n is still the number of nodes. You'll see why we use this notation in a little bit. Here's an example of S3, the star on 4 nodes. There is one node, which we're always going to label 0, that's in the center, and n-1 nodes, in this case 3, that are all connected to the central node 0 and nothing else. Here's an example of S4, the star on 5 nodes. Once again, we have a vertex in the center, which we label 0, and 4 other nodes that are all connected only to 0. As usual, our vertex set V is the set of all numbers 0 to n-1. It's also easy to describe the edge set. The edge set contains the edge 0, 1, 0, 2, up to 0 n-1. It's important to remember that we're talking about undirected graphs here. Just like directed complete graphs, which are called tournaments, there's a number of ways to orient or direct the edges for a star. Some edges could be pointing towards 0 and others away from 0. There's lots of things that can happen. So there's not really an easy way to generate the directed star. It doesn't exist. For undirected stars, though, we're just fine. Let's hop back to our editor and write a function that returns the star on any number of nodes we want. Now we're going to write a function that returns a star graph. I'll call the function starGraph, and it'll have one parameter, the number of nodes. As always, we need a docstring, and I'll scroll down to give us a little bit more room to work with here. The first thing we need to do is validate num nodes. That way, if anyone tries to do anything silly like pass a string or a floating point number, we catch it and nothing goes haywire. Next, we'll create our set of nodes or list of nodes, which again is just the range num nodes. And then we'll create our set of edges. Now for a star, every edge is connected to the center vertex, which we agreed to always label 0. So every edge is going to start with 0 and end with something else. I'll call that something else I. That number I is going to range from 1 all the way up to num nodes -1. In Python, that's just the range 1 to num nodes. So we can write this using a list comprehension by looping over every I in that range. Now that we have our nodes and edges, we'll just return the graph instance built from those. And since these are undirected, we'll set isDirected to false. And that's it. Now we have a function to return the star graph on any number of nodes we like. Okay, so now that we have a bunch of functions that can create special families of graphs for us, it'd be pretty cool to visualize them, wouldn't it? Let's hop into an interactive shell and see what these graphs look like when we visualize them with pyvis. Okay, so on the right-hand side of the screen, you can see my terminal window, and on the left-hand side, I've got a browser tab open, ready to load up the HTML file we create with pyvis. I'm going to run the graph.py file in interactive mode. And let's start by creating a path on 5 vertices. I'll call it P. Remember, to visualize the graph, we use the show function. So I'll type show P, and I'll call the output file name graph.html. All right, I'm going to quit the REPL and open up that file. And there we go. We've got the path on 5 vertices. Now, the way that pyvis works, it doesn't exactly draw it as a horizontal line. But that's okay. We still see that it's got 5 vertices, 0, 1, 2, 3, and 4. And it's got the edges going from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. It's exactly the path graph. Let's open up that interactive session again and try looking at the directed version. Let's create a new path graph called P and call the path graph function again on 5 vertices, but this time with isDirected set to true. Now I'll show P and save it to the same graph.html file as before. Now all I should have to do is refresh my browser to see the directed version of the path. There we go. We could do the same thing for cycles or complete graphs or stars. Let's look at the star on 4 vertices. I'll call it S. Now when I refresh my browser, I get the star on 4 vertices. Pretty sweet. So now you've seen how to visualize a graph data structure using pyvis. You saw how to create a pyvis network instance, add some nodes and edges to it, and then show it by saving it to an HTML file and opening it in a browser. You also learned about several different families of graphs, including paths, cycles, complete graphs, and stars. We wrote some Python functions to generate those for us, and we took a look at what some of those look like by visualizing them in pyvis. In the next video, I'll show you how to integrate pyvis with Jupyter Notebooks. Jupyter Notebooks are a great tool for doing exploratory programming. We're going to use them throughout the rest of the series in order to actually do some graph theory. And now that we have several families of graphs that we can create on command, we're in a great spot to actually start learning some graph theory. So you'll definitely want to stay tuned and check out the next video. If you enjoyed this video, please give it a thumbs up. It really helps me grow my channel. And consider subscribing if you haven't already, and hit the bell icon to get notified whenever I publish a new video. Thanks so much for watching. I'm David Amos. I'll see you in the next video.